Good morning, everybody. How's everybody doing this morning? This now is my first class of the day. So with the time change, the schedule change and all that, this is my first class of the day. So I kind of just woke up recently. So anyway, just say hi if you're there, and we'll get started. I know you guys didn't have any live stream yesterday. So how's everybody's spring break? How you guys doing? Spring break's nice. This was, for me, you guys can write about your spring break here in the comments. For me, my spring break was kind of boring. Didn't really do much. Did my taxes, did some gardening, watched some TV, played some chess. And that's about, and did some grading. I had a whole lot of grading to catch up on. But besides that, that's about it. So, I mean, it was nice to have a break. But that's about all it was. So anybody do anything exciting? Anybody at all? Today we're going to first go over those questions I gave you guys for homework. So a bunch of questions. Hopefully we won't need to go over any in too much detail, but we do have a bunch of questions to go through. And then we're going to talk about some new stuff. No, not a lot of new stuff today. I just want to take things relatively slow because we don't have any labs. Well, actually, you know what? I was about to say because we don't have any labs, but I'm going to try to set up a home lab for you guys. We'll see if you guys actually have the ability to do it. I think it'll be fun. Shouldn't be too challenging, but yeah, I think it'll be fun. So we'll see. I'll get that probably later on this week, something like that. So anyway, because we aren't doing hardly any labs, I think we are a little bit ahead of schedule. I have no idea what's going on. So with the trips and all, so you guys normally have trips, and then that also is more time away. So we're probably going to have plenty of time to finish this. So if I'm going too fast, you want to slow down or something, we can do that. If we want to have a day just to talk about stuff, review stuff, we can do that. So because I think we're going to be ahead of schedule here. Anyway, that said, let's jump into the new stuff. I don't see any comments about spring break. I guess that means it was fairly uneventful for y'all. I don't know. Anyway, let's get started. Hopefully you guys read the articles. There may have been a few questions on some of this stuff, and it's unfortunate. The day that I do this, I do a demo about pressure and all that, which is pretty cool. But anyway, hey, it is what it is. So let's just jump right into some of these questions. What is pressure and how is it different from force? The easiest way to answer this is just through an equation, and that is pressure is actually force divided by area. So pressure is related to force, but they're not exactly the same. It's going to be a force that's distributed over an area. And that's useful for things like fluids, like air and water and other kinds of fluids, because they don't exert force directionally, they exert force in all directions. So for example, when you go underwater, when you go scuba diving, the water pushes you in all directions, right? And that is felt as this water pressure, right? And so we can kind of measure that water pressure because it's force divided by the area that it touches you. So it touches you over your entire surface area. So you could actually calculate the force on your body if you know the pressure. But anyway, so that's what pressure is. And also pressure is more related, if you're talking about the ability of something to cut something, it's more related to the pressure that the object exerts rather than simply the force, right? So force is able to move things, it's able to push things or lift things, but pressure is more got to do with the ability to cut things. So a knife doesn't just cut things based on the force, but more based on the pressure. And you guys probably saw that in some of your calculations down below. All right, so we're going to focus on air pressure, gas pressure. Okay, so at sea level, air pressure is about 1 atm. That's 1 atmosphere. So 1 atm stands for atmospheres. There's a few different units of pressure that we're going to be dealing with, but atmospheres is the most important. Simply put, they're really simple, right? 1 atm is equal to atmospheric pressure at sea level. On top of Mount Everest, the air pressure is about 0.3. So you're talking about an air pressure that's less than a third of your normal air pressure. So air is essentially 1/3 or less than 1/3 as thick, so thinner than regular air on top of Mount Everest. So very, very thin air. Convert 1 atm to psi. Convert 1 atm to inches of mercury. So how we can do that, let's go ahead and do that using conversion factors. And I think your article had some conversion factors. If you couldn't find them, you could look them up. But basically, the conversion factors were this. They were 1 atm equals 14.7 psi. And that's not exact. You could get an exact number, but that's pretty close. Also, 1 atm equals 760 inches of mercury, which is the same as you may have also found 760 torr. This unit torr is identical to inches of mercury. So, if you hear about torr, inches of mercury, they're the same thing. Okay? Which also means, if you want another conversion factor, that if these are both 1 atm and you want to convert between psi and inches of mercury, well then of course 14.7 psi equals 760 inches of mercury. Okay, so those are all of your conversion factors that you're going to need for these. So you should be able to convert between different pressures, just like any kind of conversion that we've done. We start off here with 2A, that's 1 atm to psi. Well, right away, so 1 atm is 14, so that's going to be 14.7 psi. Convert 1 atm to inches. Oh, wait, we literally already just did that, right? This is going to be 760 inches of mercury. Okay, and each of these different pressure units, they sound very different from each other, so they have different reasons for what they are. Okay, so first of all, ATM, atmospheres, that's set because that's atmospheric pressure, normal atmospheric pressure. PSI is very useful for when you're doing calculations between force and pressure. So PSI stands for pounds per square inch. Well, pounds is actually a force unit, and square inches are area. So you can directly convert force and area to pressure if you're using PSI, pounds per square inch. Inches of mercury and torr, these units come from barometers. We're going to talk about barometers later, but basically, actually, wait a minute, I have that wrong. This is millimeters. I'm thinking inches, this is millimeters of mercury. So what is that in inches of mercury? My bad, nobody caught me there. Because I'm not looking at that article right now. 1 tm. So that's going to be, I don't have the article right here. That's going to be 760 divided by 254. Use 254 millimeters, or 225.4. That's 29.9. My bad. Okay, so we have 29.9. Look at this. I knew this was going to happen. Got up too late. So this should be, so this is inches, millimeters of mercury. So it should be 1 atm equals 29.9 inches of mercury. Sorry about that, guys. Yep, so 760, this is 29.9 inches of mercury. Okay, so back up here, let me see. So 1 atm is 760 millimeters of mercury, or 760 torr. That is correct, 760 millimeters of torr, and that's also equal to 29.9 inches of mercury. Okay, so where do these things come from? This 29.9 inches of mercury or 760 millimeters of mercury? This comes from a barometer. So basically, when you, we're going to talk about barometers later. You know what? Actually, let's just talk about barometers now. because I'm on to it now. So let's just talk about barometers now. So a barometer basically measures pressure using mercury and using how high mercury goes up or down. And so this is, let's just stop right here, and I'm going to draw us a barometer. Okay, so barometer, basically a very, very simple barometer, is made from a tube of mercury. And so let's just first start, so we have some tube of mercury, okay? And what we're going to do is we're going to put this into a tub of mercury, okay? And we'll just use, that's going to be too big for you guys. Let's make this a little smaller, okay. All right, sorry guys. Here we go. So let's say you have some tube. Glass tube is going to be ideal. Plastic would probably have some problems. And in this tube, we're going to fill this tube completely to the top with mercury, okay? But what's going to happen, so let's just say at a certain instant, it's filled completely with mercury. So this is Hg. This is all mercury. Okay? But what happens when you fill it completely with mercury, you have gravity on it. All right? So the force of gravity is pulling this mercury down. Okay? And so that force of gravity is pulling it down. And what's going to happen is this mercury is going to go down the tube. Even though there's going to be a vacuum up here, there's going to be no air. So if we fill it completely with mercury, completely up here with mercury, and when we let it go, it's going to go down some. All right? And you'll notice if you do this with water, it'll work the same way too, but it'll only go down a little bit. All right? And so what's going to happen is after it goes down, let's redraw this. Okay? It's going to go down to a certain level. And let's just put it like right here. Okay, and the mercury is going to come back, a little bit of the mercury is going to come back in the tub here. Okay, so the amount that this mercury comes down depends on atmospheric pressure. Well, why is that? Because not only do you have the force of gravity that's pulling this mercury down, but you also have, at the same time, you have atmospheric pressure that's pushing down here. And the pressure causes that mercury to go up the tube too. Okay, so pressure is causing the mercury to go up, and the force of gravity is causing the mercury to go down. And so at the point where those two things equal out, that mercury is going to stop. And in here, you have nothing. All right? So this is a glass tube, and you have zero air in there. So you have zero pressure in here. And this, what you can do is you can measure this with a ruler, with some kind of, meter stick or whatever. You can measure the height of this mercury, and the height of that mercury is going to be called your atmospheric pressure. So if you're in normal air, right, so this right here is your atmospheric pressure, okay? And so if you have normal atmospheric pressure going on, that measurement is going to be, so that distance, we'll just call that, we'll call that D for distance. So that distance here that is going to go up, or that height, is going to be 29.9 inches, or the distance is going to be 760 millimeters, which is 76 centimeters. Okay? So that distance we can measure with a ruler, with some kind of, whatever else. You probably have a distance measurement right on that tube. Okay? And so that is a barometer, which is a way to measure pressure, which is where this whole 29.9 inches of mercury comes from, or 760 inches of mercury, or 760 torr. That's where those numbers come from, or those units come from. They come from a barometer. And these are standard barometers, standard mercury barometers, where you basically just fill this thing with mercury and it's going to go up and down based on whatever the atmospheric pressure is. And these things are pretty sensitive. So if you have, let's say, bad weather, the pressure goes down, this is going to go down. The level of this mercury is going to go down. You can measure whatever your pressure is. Okay? So that's a barometer. Barometer. All right. Now, let's continue on. A little bit of an interruption of our homework, but hopefully that makes some sense there. And let's go back over here. Okay, so we have a conversion here. We've got 3 atmospheres. So 3 atmospheres, if we remember, that's the pressure on the top of Mount Everest, or 0.3 atmospheres. And we want to convert that to PSI. So we have our conversion factors up here, right? 1 atmosphere is 14.7 PSI. So we're going to say, okay, if we're starting with atmospheres, our 1 ATM goes on the bottom, our 14.7 PSI goes here at the top. That's going to be 0.3 times 14.7, or 4.41. 4.41 PSI. And then we also want to convert that to inches of mercury. So same deal, 0.3 ATM. And if we're starting with ATM, ATM goes in the bottom, and that's 29.9 inches of mercury. 0.3 times 29.9 is 8.97 inches of mercury. Okay, so hopefully we see now where in that world that inches of mercury comes from. It comes from barometers, ATM comes from atmospheric pressure, and PSI is pounds per square inch. So if you guys have any questions, just drop a question in the chat. Otherwise, I'm going to keep on going on. If we got 10 PSI to inches of mercury, there's 2 different ways we could do this, which are effectively mathematically exactly the same. You could convert from 10 PSI to atmospheres, and then from atmospheres to inches of mercury. But I'm going to do it a slightly faster way. So 10 PSI. And that is this. We have right here, because each of these is 1 ATM, we have right here a conversion directly between inches of mercury and PSI, right? 1 ATM is 14.7 PSI. 1 ATM is 29.9 inches of mercury. So 29.9 inches of mercury is 14.7 PSI. We're going to put our PSI on the bottom, 14.7 PSI on the bottom. Because we're starting with PSI, we want to cancel it out, so we put it on the bottom. And then we're going to put our 29.9 inches of mercury on the top. So that's going to be 10 multiplied by numbers on the top times 29.9, and then divide by numbers on the bottom, which is 20.3. Technically, we only have 1 significant figure, but I really should have given it more. Let's just say there's 3, okay? So we're going to make it 20.3 inches of mercury, okay? And let's just suppose we started with 10.0 PSI. Okay, so that's it for our conversions. Let's go ahead and check the rest of these out. We're dealing with some pressure now. Practical questions. Practical questions. Would you rather have a 300-pound man step on your foot, or a petite 125-pound woman wearing stiletto high heels, especially if those high heels are the ones with like the metal tips in the bottom? Which one would you rather have? All right, this guy is this really big guy, and this is this little woman. Which is going to hurt more? Which is going to be more dangerous to your foot? Let's find out. Let's calculate the pressure, because we remember pressure is going to be what actually can cause something to get cut or to break. So pressure is force over area, and we have 300 pounds. These pounds, in case, and unfortunately, that's part of the problem of not having class sometimes. Maybe you didn't realize these pounds, that's a force. This is force of gravity. And if you've had physics, this is old hat to you. But if you haven't, might be a little new. So that weight of somebody, that's actually the force of gravity pulling them down, right? So gravity is a force, and it depends on how much you weigh. And that weight is actually the force of gravity pulling you down. So we're going to put that in for the force here in the pressure equation. So that's going to be 300 pounds divided by, so he's stepping on your entire foot there, 8.5 square inches. All right. So 300 divided by 8.5. All right, and that's 35. And that's, notice that we can directly use, you can write pounds divided by square inches, or we could directly say, well, that's pounds per square inch. So what we're doing here is we're calculating the PSI pressure. This is 35.3 PSI. Now, that is, that's going to hurt a little bit. But honestly, that's not that big of a pressure. 35.3 PSI is definitely not enough to break skin. It's not that terrible. All right, so you can handle that. Let's check out this petite woman here. Here we go. So we got pressure is force over area. Her force here is 125 pounds, but she's wearing these stilettos with a contact area of only 0.175 square inches. So the pressure is 125 divided by 0.175. 714. That's enough to break skin. That's enough to do some serious damage. All right, 714 PSI. Well, all right, I'm definitely going to prefer that big guy stepping on my foot rather than that lady with high heels. So, practical situation here. Watch out for ladies with high heels. Don't let them step on your foot. Now, next, again, a question about pressure. Calculate the pressure that you exert on the floor. You know what? So everybody's going to get a different number. And so really, this is kind of an application where you kind of just see, how much do you weigh and what is, what's the size of your foot. You can kind of estimate that. And so let's suppose your foot, it's best to just estimate your foot as a rectangle. Okay. I know it's not a rectangle, but let's say you have a foot that's like, let's say 12 inches long, and let's say is 3 inches across. So the area of your foot is going to be 12 times 3, or 36 square inches. Okay? Let's suppose. All right? Maybe that's probably not a very good representation of your foot, but it's not going to be too bad. Okay? So you could change that for whatever it is. Now, let's first do one. So let's see. It says all right, are we back? I don't know. I'm having these connectivity issues. Hopefully this doesn't continue, because that's very annoying when that happens. So I don't know. I don't see you guys in chat right now, and just a little bit of connectivity issues. So hopefully we're back up. Anyway, so if you're standing on 1 foot, that's going to be the square, the area. If you're standing on 2 feet, so 2 feet, your area is obviously going to be twice that. So that's going to be, 72 square inches. Okay? And so then whatever your weight is. Okay? So let's suppose you weigh 200 pounds. That's going to be a force of 200 pounds. And then your pressure for 1 foot is going to be 200 divided by 36. And your pressure for 2 feet is going to be 200 divided by 72. Okay, and the answer is going to be in PSI. So I'm not going to go ahead and calculate that. Everybody's going to have different numbers. I don't think there's too many people that have the exact same numbers as this. Probably nobody. So I'm not even going to bother calculating. Next up, why does a sharp knife cut things more easily than dull knife? There's a couple different ways you could answer this. First of all, you could say that a sharp knife requires less force for the same amount of pressure, right? Remember, pressure is force over area, and pressure is the thing that's actually going to achieve the cutting. So let's suppose the amount needed to cut some particular thing is 100 or let's say 200 psi, okay? Then because the sharp knife has a smaller contact area than a dull knife, okay? That means this number is going to be smaller, and so to achieve the same pressure, you can use a smaller amount of force, okay? Or you could say it this way: because you have a smaller contact area, the same amount of force achieves a greater pressure for a sharp knife. But either way, the key is that the sharp knife has a smaller contact area than the dull knife. Okay? So, hopefully you guys are all still connected here. Sorry about that connectivity issue. Let me see. I have a little comment there. All right, so there we go. Back up. All right. So if there's no questions about any of this, let's just jump into the second page. I know we got a lot of questions here. Hopefully you guys were able to get through everything. Nothing too tricky, I don't think, but just a lot of questions. What causes air pressure? Air pressure is caused by air atoms and molecules. So mostly it's going to be molecules, but sometimes you got, argon in your air, so you got atoms. So it's going to be air particles. Particles being atoms or molecules bumping into things. Okay, and you might think, they're so small, that's not going to make a difference. Well, yes, but these small things are moving fairly quickly, and they're bumping into things all the time, and there's so many of them. So air pressure is caused by air particles bumping into things all the time. Same thing, water pressure is caused by water molecules bumping into things. So pressure, fluid pressure is all caused by these particles. They're moving around all the time. And as they're moving around, they're bumping into stuff. And when they keep on bumping into stuff, they cause a general force or pressure on the object that they bump into. So suppose you have some air in a sealed container. If we heat the air, the particles start to move faster. Yes. So those particles are now moving faster. Remember, the higher the temperature, the faster they go. How would that affect the pressure? Well, if they're moving faster, that means two things, two different things. First of all, because they're moving faster, there's going to be more collisions. They're going to be bumping into things more often. And secondly, they're going to be more powerful collisions. What do I mean by that? Because those air particles are moving faster, they're going to collide with more force. So each little collision is going to collide with a greater amount of force. And so because you have more collisions and more powerful collisions, that's a double factor that's going to cause that pressure to increase. Okay? More collisions means more force, more powerful collisions means more force, and so that's a greater pressure. Okay? Next up, suppose that you keep the temperature the same, okay? But instead you add more air. Well, if you add more air, how is that going to affect the pressure? Well, that's going to simply mean more collisions, okay? And so pressure is going to go up. More collision means pressure goes up. And I forgot to mention here, so these two things here is pressure goes up. All right, so we have an increase in pressure. If we increase the temperature, the pressure goes up. If we increase the amount of air, the pressure goes up. All right, so why don't we notice air pressure most of the time? Now this is an interesting question. Why? Because if you basically answered it based on what was said in the article, you'd get it wrong, because the article got this one wrong. All right, let me explain it this way. The article says, well, because you have, right, the air is all around you in equal directions. But that's actually wrong, okay? So how do we know that this is wrong, okay? Let's suppose that your hand gets run over by a car. And so you have a car tire that's pushing down on your hand, and you have the road that's pushing up on your hand, and your hand's getting squeezed by this car tire. Are you going to notice that your hand is underneath the car tire? Yes, that is going to crush your hand, right? And even though it's the force and the pressure is going to be the same on the top of your hand and on the bottom of your hand, it's still going to crush you. You could even think of, let's say you go down deep into the water. So you go scuba diving or something, and let's suppose you don't do anything in terms of breathing in more air. Well, what's going to happen is your ears are going to hurt really bad, and the water pressure is going to just compress you and really hurt you. So if you're a scuba diver and you go down, you need to go down slowly, and you need to breathe in more air. So your scuba tank or whatever is going to be putting more air into your system. So what does that mean? That means it doesn't matter that the pressure is the same all around you. It can still crush you. Okay, pressure can easily crush you if it's the same all around you and if it's large enough. So what's important here is not that the air pressure is the same all around you. What's important is that you have pressure inside of you too. Okay, and that pressure inside you is variable. Okay, the pressure inside you adjusts to your surrounding. So you have inside your cells, you have water, right? You have air, and you have all kinds of other molecules. Okay, those things can also exert a pressure, right? Because the air inside you bounces into things, the water inside you bounces into things. Okay, and this is going to cause a pressure that pushes back at atmospheric pressure. Atmospheric pressure is fairly significant on us. It's pushing on us quite a bit, 14.7 pounds per square inch. That's a lot. Well, guess what? There's a pressure inside of you too of 14.7 pounds per square inch, right, of a spaceship. And then you just open the door and go out into space, outer space where there's essentially zero pressure. You will explode. Okay? Why? Because this pressure inside you, you've got air pressure inside you, water pressure inside you, the pressure inside you will push out, and now it'll cause your body to blow up, literally. Okay? It won't be a pretty sight. You'll have, blood popping out of your veins because of that pressure inside you. Same kind of thing. If you go deep sea diving and you get a whole lot of air in you, so when you deep sea dive and you go down slowly, I know that is gross. Sorry about that. Hopefully you did not get any mental image. If you go deep sea diving and as you go down slowly, you breathe in air, you get more and more and more air dissolved in your blood. Okay? So the air inside you, that pressure inside you, pushes back against that water all around you. Okay? And if you go up really quickly, once again, you're going to have too much pressure inside you, and that's going to, cause you to, again, blow up. Okay? So you have pressure inside you that pushes back, and your body can adjust this. This pressure is adjustable, which is nice. And it's adjustable based on your breathing. I circled the wrong one. Based on your breathing. This air in your lungs, in your blood, in your cells. Okay? So if you go scuba diving, this is going to increase. Okay? Or if there's low pressure, it's going to decrease. And you can feel differences in pressure when you go up a mountain or down a mountain. You can hear your ears pop. And your ears popping is this adjusting for pressure inside your ears. And same goes on inside your blood. Okay, so sorry about the grossness of that. Number 11, what causes air pressure to decrease as you go up a mountain? There's a couple of ways of thinking about this. So if we're going to imagine we got, some mountains here, okay? As your little car goes up the mountain, the pressure decreases simply because you have less air above you, okay? So if we can think of air air particles all around us. Right? Air particles all around us. All right. As you go up a mountain, you now have less air above you. Air pressure essentially is caused by the atmospheric gravity pulling down on the air. The air particles are being pulled down. They stay on the earth because of gravity, and gravity causes this atmospheric pressure, right? But the higher you go up, the less air there is above you. The lower you go down, the more air there is above you. So more air above you means more air pressure, less air above you means more air above you means more air pressure, less air above you means less air pressure. So the higher you go, the less air there is above you, and the less gravity pulling down on that air, so the less air pressure. The other way you can think about this is in terms of density. So once again, because you have gravity pulling down on this air, that causes the air to be more dense down here, down at the, this Earth's surface than it is up on top of a mountain. And so as air becomes more dense, you have more air particles that are bumping into things, causing the pressure to be higher here than it is up here. Greater air density means a greater air pressure down here. Less air density means a less air pressure up here on top of a mountain. Okay. Number 12. All right, suppose that yes, and we're going to run out of time here, so I got to hurry up. Suppose your head has a radius of 3.5 inches, so we can just go ahead and calculate. I know your head is not flat on top, but we can go ahead and calculate an area, right? The area is going to be pi r squared, which is going to be pi times 3.5 inches squared. What is the weight of air above you? So let's go ahead and just get this area first. So this is 3.5 squared times pi. That's going to be the approximate surface area of the top of your head. It's going to be 38, let's just say 38 square inches. What is the weight of the air above you? Well, it turns out that you can tell exactly from atmospheric pressure, right? Atmospheric pressure is 14.7 pounds per square inch. And so if you have 38 inches of surface area of your head, that means you have 14.7 pounds for each of those. So what we're going to do is we're going to take this 38.48 times 14.7, and that's going to mean we have 566, I'll just round it off to a whole number, 566 pounds of air above you. That's a lot, right? But that's going up all the way up into the top of the atmosphere. But that's essentially how much air you have. For 38 square inches, you have 566 pounds of air above your head. Wow, that's a lot. Okay. So going quickly here, real quickly, I know I'm not going to have time to fully answer these, but what's a buoyant force? Buoyant force is just basically the force causing an object to go upward in a fluid, and that's caused because of you have a greater pressure below an object than above an object. And that greater pressure, the difference in pressure, the greater pressure below an object is going to cause an object to go up. All things have it. Every single object, not just helium balloons, but all things have this buoyant force on them, including you. But you don't go up because you weigh more than the displaced air. But there is a buoyant force on you, and the buoyant force is equal to the weight of the displaced air due to pressure being greater below you than above you. What would happen to an empty, okay, so if all the air is removed, it's going to be crushed simply because there's no pressure inside and there's a fairly large pressure outside. All right, and then this, we'll talk about that next time because I can't give you a short answer. All right, so sorry. There's a lot of questions there. But let's jump into the new stuff for today. And unfortunately, we've already answered one of the questions. And so let's go ahead and just do 2 of these other questions and then we'll be done. All right? So you guys should have found this homework. All right? So we've already answered the barometer. So what I'm going to do is I'm just going to use this space for something else. I'm going to talk about Boyle's Law. Now, Boyle's Law there's a guy, scientist named Robert Boyle, and Robert Boyle did some experiments with a barometer, going up and down a mountain with balloons, with various different things. And so he did some experiment with gases, and he noticed that as you increase the pressure of a gas, the volume decreases, or if you decrease the pressure, the volume is going to increase. So he basically noticed, Robert Boyle noticed, that the volume of a gas was proportional to 1 over the pressure. This little sign means proportional to, okay? That little sign means proportional to. So basically, as the pressure goes up, the volume goes down. As the pressure goes down, the volume goes up. They're inversely proportional. So we can get rid of this inverse proportionality by saying, okay, so volume is equal to some kind of constant over the pressure. So this is Boyle's Law, one form of Boyle's Law. Or what we could do is we could say, okay, well, what if we have, let's do it this way. Let's put all our variables on one side and put our constants on the other. So if we have the volume is proportional to 1 over the pressure, let's multiply both sides by the pressure. So that's going to get us volume times pressure is equal to a constant. Okay? Now, this we can use directly and we can calculate the constant. This constant is going to depend, it's going to change, depends on a lot of things. Depends on, the gas you have. It's going to depend on the temperature. It's going to depend on a variety of different things. Okay? So this constant is not some universal constant. So let's suppose we have a situation where the pressure and the volume are going to change. So they're both changing. But everything else is staying the same. We have the same gas and we have the same temperature. Everything else is the same. So in that case, we're going to have a before and after. Okay? So if the volume and the pressure change, well, so both of them are going to change, but this product, volume times the pressure, is always going to be a constant. So what does that mean? If the volume times the pressure is a constant, that means that the volume times the pressure at instant 1 is going to be equal to the volume times the pressure at instant 2. Because volume times pressure is always a constant, it doesn't matter what goes on. If we make any kind of changes to, let's say we change the pressure, then the volume is also going to change, but those two, that the product of volume and pressure is going to be the same. Okay? So this right here is going to be the usable form of Boyle's Law, or sometimes you might see it as P1 V1 equals P2 V2. Same thing, right? The order of those variables doesn't matter. Okay? So let's go ahead and solve number 2 here, and then we'll just close out after that. Okay? So we have 30 milliliters of gas in a piston, has a pressure of 2.75 atm. What is everything? 30 milliliters, that's going to be, so milliliters is a volume, so this is V1. Has a pressure of this, 2.75 atm, that's going to be a pressure. What is the pressure? So we're solving for P2 if the gas expands to 100 milliliters. Let me put this over here, 100 milliliters. So that 100 milliliters is going to be our V2. Okay? So we have our equation P1 V1 equals P2 V2, and we're going to solve for P2. So what I do is I'm going to rearrange the equation to solve for P2. Well, how do I do that? I divide both sides by V2. That's going to get me P2 all by itself is equal to, so the V2 over V2 are going to cancel. And you're left with P1 V1 over V2. I can plug in some numbers now. The initial pressure is 2.75 ATM. Make sure you write down your units so that you recognize, so all the units need to cancel out appropriately. Okay, so if you have two things that have two different units, you're going to need to make some sort of conversion. But here, I don't think we do have that situation. Our V1 is 30 milliliters, and our V2 is 100 milliliters. Okay? I would recommend that you do exactly what I did. Identify each of your variables beforehand, before you do this. All right? That's a very good practice to make sure you know, well, what's what are you solving for, and what is each of these different numbers in the problem. So, last of all, we can do that calculation, and then we're done. All right. 2.75 times 30 divided by 100 is equal to 0.825. 0.825. What are the units? Well, look, milliliters over milliliters cancel out, and our units are ATM, which is exactly what we would expect because we're solving for pressure. So 0.825 ATM. That's the final answer. So I'm gonna just stop here, let you guys finish up. Sorry about going a little bit over today. And this is it for homework. So you guys make sure you finish that up for tomorrow. We'll talk about the rest of this tomorrow. Make sure you have Boyle's Law. If you want, you can check out I got a PowerPoint on this on OneDrive you guys can check out. All right, anyway, see you guys. Have a great rest of your day. Oh, and a little plug here at the end. We do have a chess tournament at the end of the day today. If you're interested, email me, and I'll send you the link. Chess tournament at the end of the day today. That's going to be 3:30 today, chess tournament. See ya.